So hi guys, let's see how to draw free-body diagrams. Let's do some problems. Okay, here a block of cheese B hangs from the ceiling by rope 1. A wheel of cheese W hangs from the block of cheese by rope 2. Okay, wheel this wheel cheese hangs from B by rope 2, and this B hangs from the ceiling by rope 1. Okay, what is the correct free-body diagram for the wheel of cheese W? Let's solve it, then see options. Okay. Uh, there are different types of force actually. One is mainly is contact, two types actually. Contact forces and another is long range. Okay, just wait. Contact forces, yeah. What are contact forces? Tension, normal force, and friction. Okay, but what are long range forces? Gravitational, magnetic, electromagnetic actually, electromagnetic. But here we will mostly deal with gravitational and these contact three types of contact forces, and this is a long range forces. Okay, so that's it, you remember it and you understand, that's it. Now let's see. Yeah, you know the rules to draw the diagram. Free body diagram is considered the object which is of our interest. Here W is our interest, then outline the object boundary. So we have already outlined the object boundary. Now find the contact force, find all the points where any type of other object or thing are putting force on this object. So here it is touching rope 2. So here there is a force. So what do you do? So you just draw a vector from the object towards the direction of force and where the force is directed, and the length of this arrow should be according to the scale of magnitude of the force. Let's say it's pulling in 5 newton, and down there is 10 newton of gravity. So you do this, you don't this is 10 newton, so these arrows are by scale according to their magnitudes and direction. So here, okay, there's one tension, okay, FT maybe. Okay, there is another force which is down. This is contactless force. We draw the boundary to find the contact force, but we know that there is a contactless force, that is long range force, which is gravity. So this is FC. So that's it. That's the free body diagram of W. Okay. So let's see. Yeah. So these are the symbols here used. Normal force, force of gravity on block B. So this is, so we have GW. Okay, that's it. So there will be only two forces. Wait. Yeah, only this one. That's it. Next problem. Hmm. Yeah, the carrot hangs from the ceiling by two ropes, one and two. Okay. Yeah, we see the carrot is hanging from the ceiling. What is the correct fever diagram for the carrot? Okay. To find the fever diagram, what do? You just outline the object. Okay. The object boundaries. This is the object boundary. We outline this. Sorry. So here one contact, here another contact. So two contact forces. So you just do like this. Doesn't matter. Pivot diagrams. So actually here is, see, the weight distribution matters, but here you just do by, you know considering this as a normal cylinder like things. Okay, so it is, let's say, ft, and this is f1t ft1 maybe. This is tension to ft2, whatever the symbols are. And another is downward, the gravity, the contactless, the long range force, which is fg on carrot. So this is it, three forces only. Let's see. ft1, yeah. Yeah, this is it. A block, now next question. A block of cheese is pulled on by a string and slides to the right along a rough surface. So this is a rough surface. So friction will be there. What is the correct free body diagram for the block of cheese? Okay. What is the block of cheese doing? Okay. So first thing what we outline the object's boundary. Every, yeah, I took a bite here. Okay. Okay, here is a force by the string ft. Okay, the tension force from here. Okay, so this is a contact force. Another contact force is normal. Ooh, Fn. Another contact force is the wait. This is not contact force. Another the contactless force is only is gravity. So Fg. So now another, as it's pulling here, so the block is moving to the right, let's say. It doesn't matter if it's moving or not, but there will be a contact force of friction. So this is it. That's the 3D diagram. Let's check. There are four forces. Four forces for friction is called. This is it. That's it. A curve is sliding down an inclined surface that is not smooth. Okay, not smooth means friction will there, and it's sliding down. Okay, what is the correct figure diagram for the curve? Okay, just first thing first, outline the object boundary. I neglected the handle. It's fine. I mean, there is no contact here too, so it doesn't matter. So here, force of friction opposite to the motion. Gravity is always down. In from the middle, we have to take. We have to consider actually this object as a point. It's called center of gravity actually, not the center of mass, but it's fine if the body is uniform. So gravity and center of mass will, I mean, if the object is made of one type of material, the object, so the center of gravity and center of uh, mass will be coincided. If it's not too big, so yeah, so it doesn't matter. So the friction is here. Okay, from friction is from down, but if this is from here, the contact force is from here to upward. Fn. That's it. That's three things. So as you are just studying, you know, you're just starting it. So you can do this. You can draw by this. When you go along the courses, you will have to consider torque, all those things. So You have to consider this the distance also. But here we will just do this. Consider the object as point and the process will be like this. Otherwise, if the copy is shown in the option, we'll see this thing will be the answer. Otherwise, we'll do this anyway. But actually, this is the correct. Anyway, let's see. Okay, he considered it a big point, and he didn't show where the forces are ending, starting and starting. Anyway, so friction would be opposite. This is not correct. Yeah, this is. So that's it. Thank you. So hello, guys. Let's see three problems on Newton's first law. These are some interesting problem, and your concept will get clear. Okay, let's start. Example one: space probe drift problem. A space probe is drifting to the right at a constant velocity in deep interstellar space, far from any influence due to planets and stars. Okay, with its rockets off, if two rockets thruster both turn out simultaneously, exerting identical force, okay, leftward and rightward in the direction shown, what would happen to the motion of rocket? Okay, so this probe was drifting rightward, like going at a constant speed, rightward. Then at this moment, when this space probe reaches this point, whatever the time t is, suddenly the two thruster get turned on. So they both give equal thrust. It is given in the question. So at this point, there will be no net force actually. There will be a force rightward due to left thrust, and there is a force this leftwards due to this right thruster. So no net force. What Newton first law says, body would continue its state of rest or state of motion with a constant velocity unless it is acted by an external force. So there is no net external force. The net external force is zero here. So it will continue with constant velocity. The answer is what? A is the answer. No, it won't speed up. It won't slow down. No, immediately. If you were to, if it was stationary before, then D option will be correct. So only A option is correct. The correct answer is this is the reason. Okay, you can read it. Let's see example 2. An elevator is being pulled upward with constant velocity. So constant velocity. Constant velocity means no net force by a cable as seen in the diagram below. While the elevator is moving upward at a constant velocity, how does the magnitude of upward force exerted by elevator on the elevator by the cable compared to magnitude of downward force of gravity? So as you see, it is moving in constant velocity, so no net force. So Fc should be equal to H. That's it. B, option B, C. You can read it. That's it. Now example 3, space probe path. A space probe is drifting, example 3, to the right to the constant velocity in deep interstellar space, far from any influence due to the way. If a rocket thruster turns on then off for a short burst force, uh, then off for a short burst of force in the direction shown. Okay, if the thruster opens here, so the force should be downward. What would be the best represent path travel? What would best represent the path traveled by rocket after the thruster turns off? Okay, after the thruster turns off, what would be the path? Is D or C or B or A? Which path do you think the rocket will choose? After the thruster turns off, if you'd ask while the thruster turn remains turned on, then this option would be correct. not this actually. There is an option like that, but the path would be like this, like a parabola. But here he says the thrusters turn on and then off for a short burst of time. So after the thrusters turns off, the rocket the rocket will, whatever the space probe, will gain a vertical velocity in this downward direction. So I mean this okay, downward direction, whatever. Uh, so, but there are, according to Newton's law, there is no net force along the horizontal direction like this. So the velocity of the space probe along the horizontal direction will remain same. So it will remain continue to move like this, but it will also gain speed along vertical direction. So the path would be a straight line like this. C. So path C. So option C is correct. That's it. This is the reason. No net force. Once the net force is zero, you can read it. Yeah, that's it.